Welcome back to this course on multi-core architectures. The topic of this lesson is extensions to the basic MSI cache coherence protocol that I presented in the previous lesson. These extensions reduce the amount of communication that has to take place on the bus for certain common sequences of CPU requests. As usual, the source of this lesson. It is based on section 5.2 of the textbook by Hennessy and Patterson. I want to explain the MESI protocol to you, which is a very common coherence protocol used in many multiprocessor systems. Before I do that, however, I want to give a brief motivation for it. Consider this very common sequence of CPU accesses. At time t1, thread 1 reads A and then writes A, and after that at time t3, thread 2 reads B and then writes B. Let's consider now what will happen when we employ the MSI cache coherence protocol, assuming that initially the block containing A is invalid in the cache of processor P1 and the block containing B is invalid in the cache of P2. At time t1, thread 1 reads A. Since it is not present in its cache, a read miss for A will be placed on the bus, and the block will be brought to the cache of processor P1 from memory in state shared. Then at time t2, thread 1 writes A. It is in state shared in its cache, so there might be other copies. We don't know, which is why an invalidation must be placed on the bus to invalidate all other copies. Thereafter, the block containing A will be in state modified in the cache of P1. But is this invalidation really required? Well, I think not really, because there are no other copies of the cache block. The MSI protocol doesn't know that, however. Next, at time t3, thread 2 running on processor P2 reads B. Identical to what happened when A was read, P2 will incur a cache miss and fetch the block containing B from memory in state shared. Finally, at time t4, P2 writes B. Again, there might be other copies of B, so an invalidation message must be placed on the bus. And again, this invalidation message is not really needed since there are no other copies of B. Bottom line, both invalidation requests for A as well as B were unnecessary since there are no other copies of A and B. These considerations have led to the design of the MESI cache coherence protocol. In the MESI protocol, there is one extra state called exclusive in addition to the states M, S, and I. The exclusive state means that the block is present in exactly one cache and is clean, meaning that the copy in memory is up to date. Because the block is present in only one cache, the corresponding processor can write it without having to invalidate other copies. So the MESI state transition diagram includes this transition from the exclusive to the modified state. I will not show the entire MESI state diagram, but only the parts that are really different from the MSI diagram. The construction of the entire MESI state diagram is a useful exercise for you. However, when the cache controller snoops a read miss to a block that is contained in its cache in state exclusive, then the state of this block should become shared, since now there are multiple copies. Furthermore, now there is a choice. Either this cache or the memory can return the block to the requesting processor. In the baseline MESI protocol, it's the memory that returns the block, and I will assume the same. One of the reasons the MESI protocol is so popular is that it works very well for multi-programmed workloads, which still is the majority of the parallel workloads today. In a multi-programmed workload, the cores run different processes that never or rarely communicate with each other. So there is no sharing of data, which is why other copies do not have to be invalidated since there are none. The Intel Core i7 actually uses a variant of the MESI protocol called MESI. In this protocol, there is an extra state called forward, which indicates the core that should respond in case of a read or write miss. In fact, this is very similar to yet another protocol called MOESI. Before I describe that protocol, I will again motivate it using a sequence of CPU accesses and showing the behavior of the MSI protocol on that sequence of accesses. Consider the sequence of accesses shown here on the left. Thread 1 reads A and then writes A, then thread 2 reads A, and finally thread 3 also reads A. As before, in this table on the right, I will illustrate the behavior of the MSI protocol, assuming that A is initially invalid in each of the 3 private caches. First, thread 1 reads A. It will incur a read miss, places the corresponding request on the bus, and the state of A in the cache of P1 will be shared after this transaction. At time T2, thread 1 writes A. It has a copy of A in state shared, so needs to invalidate other copies, and the state of A changes to modified in the cache of P1. Then at time T3, thread 2 reads A. It doesn't have a copy, so it places a read miss on the bus, and the cache of P1 will return the copy. After this transaction, A will be in state shared, both in the cache of P1 as well as in the cache of P2. Finally, at time T4, thread 3 also wants to read A. The cache of P3 again doesn't have a copy, so again a read miss is placed on the bus and memory will return a copy of the block. So what can be improved here, in addition to the write of A at time T2, which can be improved by the exclusive state? Well, at time T4, the cache block is returned by memory in the base MSI protocol. The cache of P1, however, or the cache of P2 for that matter, could also have returned the block, and since the cache access time is always shorter than the memory latency, either option would have been faster. This observation led to the design of the MOESI protocol, which adds one extra state called owned compared to the MESI protocol. The owned or O state means that this cache has a copy of this block, but there might be other caches that also have a copy of this block, but in state shared. Furthermore, the memory copy might be outdated. So if another cache requests this block via a read miss, one of the caches, not memory, should reply. Which cache should reply? Because it wouldn't make sense if all replied. Well, that's exactly the purpose of the owned state. The cache with the block copy in state owned replies. So at any time, only one copy should be in state owned. And when the corresponding cache controller snoops a read miss to this block, it will supply the block and abort the memory access, as illustrated in this state diagram on the right. Another advantage of the MOESI protocol is that the cache controller does not have to write back the block to memory when it snoops a read miss to a modified block. It can simply change the state of this block to owned. It does mean, however, that when a block in state owned is replaced, it needs to be written back to memory, since the memory copy might be outdated. The AMD Opteron processor line actually employs the MOESI cache coherence protocol. This concludes this lesson. Thank you for watching. In the next lesson, I will discuss some limitations of symmetric multiprocessors, SMPs. Stay tuned.